Hi there, my name is Chris, and the video I'm making today is explaining the topic. Given the KEQ and initial concentration of reactants and or products, calculate the final concentration of reactants and or products. So I'm going to work through a couple of examples here for you guys. Get this set up here. Okay, so our first off, we have our KEQ, which is also equal to KC, so you might see it written as that. If this is the equation we're given, the KEQ is equal to the concentration of the products divided by the concentration of the reactants. And each of them is raised to the power of their coefficient. So if this is the coefficient and this is the chemical symbol, then we would take the chemical symbol and then we'd raise it to the power of the coefficient if there is one. So the first example will work here. So this is the equation that we're given, and we're told that 1.34 moles of each of the products is added to an 11-liter flask. This is our Kc value that we're given, and we are going to calculate the equilibrium concentration of each of these. So I'll work this problem, and then I'll work a couple more. So this will be a little bit longer of a video, but just put me at 2 times speed and it'll go a little bit quicker. So first thing that we need to do is we need to calculate the concentration. So we're given moles and we're given liters. Moles over liters is our concentration. So we have 1.34 moles divided by 11.0 liters. And I'll take my trusty calculator over here. 1.34 divided by 11 is going to equal to, we'll just call it 0.12. We'll round to 2 sig figs here. And then that is capital M molarity. So 0.12 m, 0.12 m. So we'll go ahead and erase this. And just be careful that we're not using moles for our concentrations, because then that's going to just throw off your whole problem. So on the final especially, just make sure that we're starting with what we need. So now we have our initial concentration, we're going to have our change, and we're going to have our equilibrium concentrations. We'll set up our ice box here. So we started with 0 of this because these things here were added, and then we're going to establish the equilibrium. So we're going to have minus x of each of these because the coefficient is 1. We're going to have 2x of this because we've got this 2 here. So now we add all these together. So we have 2x. For both of these we have 0.12 minus x. And then we'll do our equation like this. So we have our concentration of these, and since it's the same thing, I'm just going to square it. So 0.12 minus x squared over 2x. And then that is also going to be squared because we've got this coefficient here. And then that all is going to be equal to our Kc, which is 0.143. Now, since both of these are squared, that makes things a lot easier for us. We can just square root both sides. So now we have 0.12 minus x divided by 2x equals the square root of 0.143. Oops. 0.3, I'll just say 378. And then we multiply both sides by 2x. So we get 0.12 minus x equals, we'll just take that times 2. We'll say 0.756x. And then we'll add an x to each side to get our variables on one side. So we have 0.12 equals, well, this is just plus 1, so 1.756x. Divide both sides by 1.756. We'll then get x equal to, so here that's, and we'll do plus 1, so now that's on our calculator, and then we can take 0.12 divided by our answer. We get 0.068, we'll just say 0.07. So now we can take this up here and we can plug this back into our equilibrium concentrations to get those numbers. So we'll take this times 2, so we have 0.14 m is the concentration of our reactant here, and then for each of these we'll just take 0.12 minus 0.07, and we'll get 0.05 molarity for each of these. And then of course we can say, concentration of bromine gas, chloride gas. You can write all that out, make it all look all nice, but that is how you get to that answer if we're given the concentration, the initial concentration of our products. Now, what if we are given the initial concentration of our reactants? So we'll go over here to this one. So here, this is our Kc value, and we are given the initial concentration of our reactant here as 0.100 molar, and then we have 0 of this, and we just have 2 of them here, or just one reactant and one product. So we'll do the same thing. We'll set up our ice table here, and then this one we're going to go minus x, and then this one again we have a coefficient, so that is going to be 2x. So when we add all these, we have 0.100 minus x, we have 2x. And then we have our Kc value. So then our Kc value, 0.36, is going to be equal to the concentration here, so 2x, and then that's going to be squared because we've got that coefficient, divided by 0.100 minus x. And normally we would be able to simplify this, but since our Kc is actually quite a big number compared to our initial concentration, we will not be able to do that. So we're going to multiply all this out, so we'll multiply both sides by 0.100 minus x, and then that is going to give us times the negative x here, so we'll multiply this, so we have negative 0.36x plus 0.036 equals 2x squared, and I think we can see where we're going here. We'll get all of our things over here to get it equal to 0, 2x squared plus 0.36x minus 0.036. Then everybody's favorite, the quadratic equation, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So that is going to be equal to negative 0.36 plus or minus the square root 0.36 squared. And I'm just going to kind of write this out, and I've already done the math, and I'll save you guys all of that. But I'll just kind of show you where these numbers plug in here. All over 2a. So that all ends up coming out to equal x equals 0.0716. So then we can go back up here. So the concentration of our NO2 gas is going to be 2 times x. So we'll go 0.0716 times 2 equals 0.14, and we have 2 sig figs here, so we'll just stay with 2 sig figs here, 0.143, so we'll just say 0.14 molar, and then this concentration is going to be 0. Can we see my calculator? Good deal. 0.100 minus our x, 0.0716 equals 0.0284, so we'll just say 28 molarity. And then we can double check that it was a good idea not to simplify, so we can take our x value, 0.0716, divided by our initial concentration, 0.100, times that by 100. So I'll show you that here. So we'll take 0.0716 divided by 0.100, and times 100. That equals 71%, so that was definitely, it needs to be less than 5% to be able to simplify, so 71 is not less than 5, I think. I don't remember that from elementary math, but we'll assume that that's true. So this one was a good one not to simplify, so we'll have to do the quadratic equation. Now I'll show you an example where we are going to simplify. So here we have this equation, and we are given our initial concentration of our reactant. So we have 0.25 molar. So we'll set up our ice box. So here we did an example where we were given the initial concentrations of our reactants. Here we were given the initial concentration of our products with the quadratic formula. Here we're given the initial concentration of our reactants once again, and then I'll show you this one we'll be able to simplify because our Kc value here is much smaller, and we'll do our double check as well. So here we've got two reactants. We have a gas and we have a liquid. So liquids and solids are not included in equilibrium concentrations because we don't look at them in terms of concentration, so we'll actually leave that out, so we'll just ignore that. So we've got 0.25 molar, and then we have none of either of these. So then we will say minus x for our change here, and then x and x. So then we have 0.25 minus x. We've got x for each of these. So now we can set up our Kc is equal to concentration of the products divided by the concentration of our reactants. Kind of skip this part over on these other ones, but this is what we're doing here. So we have 1.8, I use the e to the negative fifth, equals x squared, because we got both of these multiplied by each other, divided by 0.25 minus x. Now, since our Kc value is so much smaller than our initial concentration, we're just going to assume that we can simplify. So then we've got that. So now we have x squared is equal to, and then what I'll do is I'll just go ahead and take the square root of these. So in my calculator I'll just do square root of 1.8 times 10 to the negative fifth times 0.25. That just kind of skips a step here. So then that gives us x is equal to 2.12, we'll just leave it there, times 10 to the negative third. Now our double check, we'll take the x value we got divided by our initial concentration, just like we did over here. So divided by 0.25, we'll multiply that times 100, and we want that to be less than 5%. So we'll just leave that in the calculator here, divided by 0.25, and then we'll take that times 100, and we have 0.84%. So that one is okay to simplify. So now we've got our x value, so we can take these two concentrations are going to be the same, so we'll just say that that is equal to our x value, so 2.12 times 10 to the negative third molarity. And then this one here, we had 0.25 minus our x, so we have 0.25 minus 2.12 times 10 to the negative third. So our concentration of that is going to be 0.247, and if we're just going to do, we'll do two significant figures here, so this would actually be 2.1, 2, so 0.25. So again, you can see that this was okay to simplify because it ends up being 0.25 anyways. And that is how you can find the equilibrium concentrations of different reactants and products if we're given the initial concentration of our products or the initial concentration of our reactants, and we're given the Kc value on each of these. And then here's, I did an example, one with the quadratic formula so you can see not to simplify, and then one where we could simplify, so we've got that as well. Hope that helps. Good luck to everybody on the final.